Hi, I'm Ali Haider and I'm from Chemical Engineering Department at Indian Institute of Technology in Delhi. I teach mostly chemical reaction engineering and I do research in heterogeneous catalysis, molecular modeling of catalytic reactions. We apply both theory and experiments in teaching catalysis, and I do a lot of experiments combined with theoretical approach in understanding reaction mechanisms, how catalyst functions at the molecular level. So, this talk I have prepared to bring up some new ideas in catalyst design which can be applied in industrial reactions. So, that is the new frontiers of research which are explored these days using theoretical and experimental approach. So, some of the ideas and concepts are taken from undergraduate textbooks and how you can apply the new ideas on catalyst design where you can use some of the theoretical approach and apply this to industrial catalysis. So, this talk I have prepared on optimal catalyst design in adiabatic reactor operations. Let us start with the beginning. The idea of a catalytic cycle is really interesting because the reactions are happening on a heterogeneous catalyst surface. So, for this you need reactants to first adsorb on the catalyst surface, then it will go for some diffusion or go around, move around, and then there will be a reaction, and from there you will have surface reaction and then more diffusion moving around, and then you will have desorption of the product. So, you have to complete the whole cycle. Things should adsorb on the catalyst surface, then they should react on the catalyst surface, and then things should desorb from the catalyst surface. So, this whole idea is all about how many times you are going to turn over this cycle. So, things should also adsorb and things should also desorb from the catalyst surface. So, intuitively you can think about, let us say if you are adsorbing something really too much, then the surface will cover up, there will not be any desorption happening and things will be sticking on the catalyst surface. So, you can't turn over the cycle. And let us suppose if you are desorbing and things are not coming and adsorbing properly on the surface, then you will have a neat and clean surface, but things will not be reacting on the surface. So, you need an optimum here that things should adsorb at the optimum binding and as well as desorb with an optimum binding. So, you need an optimum scenario where the whole cycle should turn up, things should also adsorb and things should also leave the surface once the product is formed. So, this whole idea of catalytic cycle is getting that optimum, and if you really think about this, that is how Sabatier 100 years ago actually thought about it, that if you are really thinking about how a catalyst can function better, you have to think about a descriptor or a bond strength of your key intermediates which are adsorbing on the surface and which are reacting. So, that bond strength has to be optimum. If that intermediate is binding too strongly, then you are limited by desorption of the products, or if this is binding less, then you are limited by the activation of the reactant. So, you are either, if you are binding too strong, then things are covering the surface, and if you are not able to bind them strongly, then they are not, the reaction is not happening, the things are not coming on the surface. So, you actually need to get into the optimum, and there you will get a Sabatier optimum. If you get that binding correct, then the catalyst cycle is completed and you get the maximum turnover, and that is the rate turnover frequency, and that gives you a Sabatier optimum. So, this is the idea, the holistic idea of designing a catalyst surface is that you think about how you can achieve that optimum binding of the intermediates, the key intermediates, and those key intermediates are known as the descriptor in a catalyst cycle. So, you want really the cycle to turn over and you want the right optimum here where you will get the reactivity, the maximum reactivity. So, that is the idea. We will try to apply this idea how you can design catalyst surface. For example, the next concept introduced recently is about interpolation principle. So, let us suppose you think about ammonia synthesis and we know about nitrogen bond. So, nitrogen is a very difficult bond to break and it requires a really high energy to break it. So, and the key descriptor here in this reaction, for example, if you start with nitrogen, it has to break and it has to form adsorbed nitrogen atoms on the catalyst surface. Then these nitrogen atoms has to hydrogenate with adsorbed hydrogen ones on the surface to form NH. Then these NH needs to form NH2 and NH2 needs to form NH3, and then NH3 needs to dissolve. So, all of these are surface reaction steps, and this one is adsorption, and this one is NH3 star going to NH3 in the gas phase. So, this is desorption. So, all of this will complete the whole catalytic cycle, and in this you see the first step usually is rate determining. The first step is usually likely, or I will say likely rate determining step. So, in this reaction, if you will see, the key descriptor is how the catalyst surface is binding nitrogen. So, if you have the catalyst surface like this, the key descriptor here is how it is binding the nitrogen atom on the surface. This nitrogen should be at optimum binding, not very weak or not very strong. So, this is the key idea, and if you think about that, you will come back to this Sabatier plot. So, we have certain elements like iron and moly, they are binding very weak, or they are binding really strong, and then you have nickel and cobalt, and they bind relatively weaker. So, you have the green region which is binding weak and the blue region which is binding strongly. So, there are certain elements which are really active like ruthenium and osmium, and these elements are active because they get the binding correct. So, they have the binding in the right region in the middle, which is around the Sabatier optimum. And if you want to get there, let us suppose you can combine metals. For example, ruthenium is really expensive, you want to make some cheaper metal alloys or something, you want to get exactly at the binding in the optimum. So, interpolation principle explains that if you take one element from the stronger side, let us suppose you take moly here, and if you take one element from the weak side, let us suppose you take cobalt, and you mix them two together. So, do not mix iron and moly because both are on the strong binding sides. You try to mix them, iron with some weaker one or moly with a strong weaker one like moly and cobalt here, then you can possibly get to the Sabatier optimum. You can get the maximum turnover frequencies because you are mixing two metals, one with weak binding energy and one with a strong binding energy. And this is the concept of designing or rationally designing a catalyst surface using interpolation principle, which can be applied in getting the desired reactivity for in many reactions. So, that is what has been recently shown, and all of this can be done now using density functional theory approaches. So, all these nitrogen binding sites on these catalyst surface can be calculated by density functional theory. Even turnover frequencies for ammonia synthesis can be calculated theoretically. So, all of these design idea can be all constructed from theoretical approaches. So, you do not need to perform experiments, but once you design a new surface which gives you the right binding on the volcano plot right on the top of the Sabatier maximum, you can test it. You can probably synthesize these catalysts and you can test it for your theory whether it is working or not, but in most cases people have found that this is working. So, this is really amazing that you can design catalysts from ab initio DFT theory and you can make something work. I will give you one more example, which is hydrogen peroxide decomposition. This reaction is tried actually in many undergraduate experiments and CRE laboratories. So, you have H2O2 decomposition in presence of a catalyst, and this will produce oxygen, and oxygen is trapped or collected. So, this is here the oxygen is coming and you have this reaction going on. Let us suppose you do this reaction with several different catalysts under similar reaction conditions. So, you try nickel, copper, platinum, silver, gold and titania. So, several metal catalysts and one oxide catalyst, and you measure catalyst activity, which is you are measuring the millimole of oxygen produced per meter square per second. So, you are pretty much measuring the turnover frequencies, how many times the catalytic cycle of H2O2 coming on the catalyst surface is producing oxygen as the product, and you are doing this and you are seeing how do you relate the activity of all these catalysts together. So, here the key descriptor in H2O2 decomposition is hydroxyl binding energy on the surface. So, if you get the hydroxyl binding energy calculated from theory using density functional theory calculations, So, by just calculating the adsorption energy of hydroxyl on these catalyst surface, you can correlate the reactivity of all of these catalyst materials, and you can correlate them and you can show it in the form of a Sabatier plot, which is shown here. You can see how nicely these catalysts align in the form of a volcano plot, which is showing that at the Sabatier maxima you obtain platinum. So, platinum is active because the binding is correct for hydroxyl, and that also tells us that the hydroxyl is the key descriptor. The binding energy of hydroxyl is the key descriptor in this reaction. So, if you can design some, let us suppose bimetallic, you want to combine two metals and you get the right kind of hydroxyl binding on the catalyst surface, then that will give you catalyst may be cheaper than platinum. You can get a catalyst which can be really cheap, combination of metals by using interpolation principle, and you get the catalyst exactly behaving like platinum. So, that will save a lot of cost. So, these are the simple ideas by using theory, that you calculate the binding energy of a key adsorbate on the catalyst surface, and you can correlate with the reactivity of several catalysts. Here we are showing it is correlating with oxides as well as metal catalysts. So, this is really interesting ideas from theory perspective. Now, we come back to our old understanding, which is undergraduate understanding. Those who have taken classes from chemical reaction engineering understand Fogler or kinetics and non-isothermal reactor design. They might recall this. Some of these concepts are coming from 10+2 understanding of reversible reactions. So, here is a reversible reaction, A going to B, and let us suppose I change the temperature of this reaction. We know that if it is an exothermic reaction, we can calculate the conversion of A, and that will drop down with increasing temperature. So, that is by Le Chatelier's principle, which explains that the conversion of a reactant will go down as you increase the temperature, because the other side you are producing heat. So, the reaction will go backward, and this is the idea which is very preliminary idea from undergraduate understanding. This curve you can plot using a Van 't Hoff equation, how equilibrium constant is changing with respect to temperature, and conversion is basically here for this simple reaction is equilibrium constant divided by 1 plus k. So, by this equation you can get, and k as a function of temperature is given by Van 't Hoff equation. So, you have equilibrium conversion dropping down with respect to temperature. So, this is the maximum conversion you can get in an exothermic reaction, because this is your thermodynamic limit. You will always run the reaction beneath this limit of conversion. So, this is your maximum thermodynamic envelope under which you are doing all these reactions. Now, let us suppose you are doing an exothermic reaction in an adiabatic reactor, and you do energy balance on this reactor. The simplest form of the energy balance here is that conversions will be equal to Cp, which is the sum total of all these molar capacities of heat, and then multiplied by delta T, the change in temperature. For example, here is T2 minus T1 divided by the reaction energy at temperature T2, and you can assume that reaction energy is not changing. So, then it is just the reaction energy, and you can divide it by that. So, here the conversion, if you see for an exothermic reaction, the delta H will be negative. So, overall slope of this line will be positive. So, here you will see the adiabatic energy balance is guiding that the reaction should follow a path which is a straight line. So, the reactor operation usually follow a path which is a straight line. So, x is always increasing with T. So, Le Chatelier's principle is guiding that at exothermic reactions the conversion is always dropping down with increasing temperature. Here for adiabatic reactors, by energy balance what we are getting is kind of like reverse of what equilibrium operation is telling, that conversion is always increasing with respect to temperature. So, these two conditions has to satisfy in a reactor, and when they satisfy, that is the point you usually operate in an adiabatic equilibrium environment. For example, here you have two equations, one is coming from energy balance and the other is coming at the equilibrium, and where these two lines intersects, that is the point you operate your reactor, adiabatic reactor at equilibrium. So, both these conditions needs to satisfy in order to meet equilibrium adiabatic conditions. Okay. So, where you solve it. So, if let us suppose you have the feed temperature T1 and you start your reaction in the adiabatic reactor, since the slope is given by Cp upon delta HR, so which is pretty much constant, you are not adding anything, or you are not changing the reaction energy. So, slope of this line has to be constant. So, then the line has to meet the equilibrium envelope at max here. So, if you are getting this is X A equilibrium, let us suppose this is looking like 50%. So, if it is reaching up to 50%, it is not going to go more than that. Okay. So, no matter what you do, you are not going to increase convergence more than 50%, and that also you are meeting at equilibrium. You are not going to run your reactor at equilibrium because the rates are 0. So, here you are trying your best, but you will reach maximum up to 50%. So, the engineering idea around this is that you can change the feed temperature. So, for example, instead of starting at T1, you can start at T0. Since the slope is constant, it will go further, but this time it may reach higher convergence, okay, because the line will meet equilibrium at a much farther point than the point before. So, then you have a higher conversion as compared to what you would have obtained earlier. Okay. So, by changing the feed temperature, you can shift the line up and down in parallel to it, so that you can increase the convergence. So, that is one idea, that you can shift the line up or down and you can achieve higher convergence. Okay. So, this is one idea. The next idea which is applied industrially is known as interstage cooling. So, let us suppose you want to run this reaction in an adiabatic reactor, and this is an exothermic reaction. So, let us suppose you do this reaction and you have feed at 500 degrees centigrade, and this reactor is adiabatic, and after doing this reaction you have whatever is coming in output is about at 800 degrees centigrade. So, T2 is 800 and T1 is 500. So, you started at 500 and you went up to 800, and that is the point you have reached. So, if you keep continuing, you will meet the equilibrium envelope, and that is the maximum conversion you can get. So, you take the feed out at 800 and you apply an interstage cooling operation, you cool it down further back to 500 and you bring it back to 500, and then this way on the operating line you will go back to 500 point straight back, and then you will start again. You apply another adiabatic reactor operation. So, you use another adiabatic reactor in series and you do the reaction same, A going to B, and then you keep doing this reaction. Let us suppose it gets to 700 degrees centigrade, and here you apply another interstage cooling operation. You go back in line and then use another reactor for the same reaction. So, in this way you are applying 3 reactors in series, and intermittently you are applying an interstage cooling operation. This way you are trying, what you are trying is, instead of reaching to a lower conversion value, you wiggle around, you go back again on the adiabatic reactor line, you wiggle around again, you apply interstage cooling operations, and this way you move towards higher convergence. So, this is a very applied concept which is used in industries and using several adiabatic reactors in series, and many reactions are run this way, which are exothermic reactions, to get higher convergence. So, the whole idea is that you apply several adiabatic reactors in series and you wiggle around, and so that you can reach to higher convergence. Now, the next concept is about rates. Okay. So, if you can see this graph earlier, you really do not want to reach at the equilibrium. You want to stop before the equilibrium, because if you reach the equilibrium, the rate will be 0. So, you want to run the reaction at some net rate. So, you want to achieve, or you want to get some rate of reaction while you are operating reactors. So, you want to get some net rate. So, you really do not want to go all the way up to equilibrium envelope and then apply an interstage cooling operation. You want to go there and you want to stop a little bit before it and then apply an interstage cooling operation. So, the question is where you want to stop it and where you really want to wiggle around, and so that you can reach higher convergence. So, the idea here is that you have an x versus t plot. The outer envelope is the equilibrium envelope. We saw that it can be obtained from equilibrium constant, how equilibrium constant is changing with respect to temperature. Now, you can plot the inner envelopes, for example, at a constant rate of 1, 10 or 100. These envelopes are plotted. For example, you can calculate the net rate, which is the rate of forward reaction minus the rate of backward reactions, and both rates have a net rate constant, which is Kf and Kb. So, Kf upon Kb, and that is how there is a competition between them. When you increase the temperature, both rate constants are increasing by Arrhenius law, and then there is a competition. So, when there is a competition, the net rate goes to an optimum and then comes down. So, you have the lower rate here, then you have R is equal to 10, and then you have R is equal to 100, like that. So, you have higher rates at higher temperature and lower rates. So, you start from R is equal to 0, which is at the equilibrium, and then you have increased rate envelopes beneath it. So, in these envelopes, you can imagine that there could be a possibility of running the whole reactors at maximum rates. Okay. So, you want to run or you want to wiggle around on these rate envelopes, so that you achieve maximum rates from your reactor operation for the rates. Okay. So, that the strategy here is that you start your reactors at the maximum allowable temperatures. Okay. You want to start where the maximum temperature which a reactor can be operated, whatever is the limit of the material or construction of the reactor, and you want to operate on this line, which is the locus of maximum rates, which is going on top of all of these rate envelopes. Okay. So, at each point you are actually getting maximum rate. So, on each envelope you are setting for the maximum possible rate you can get at that point. So, you do not want to run at equilibrium envelope, but you want to run a line beneath it, which is known as locus of maximum rates, which is the best path of operating an exothermic reaction in adiabatic reactors. Now, you are this is all coming from material balance. So, you want to run the reactor here, but adiabatic condition is saying that there will be a slope of line which will be positive, and the reactor also needs to follow the energy balance. Okay. So, you have all these conditions should meet together to give you the best performance in these operations. So, how you are going to get it? We will plot it here. Now, I am showing you here. For example, this is ammonia synthesis. So, nitrogen and hydrogen are making ammonia, exothermic reactions. So, the outer envelope here is the equilibrium conversions, below which, as I said, there is a line of maximum rates. Okay. So, you have line of maximum rates, you want to start the reactor such way that it reaches to the line of maximum rates. Now, you want to apply interstage cooling operations, and you want to apply in a way that you wiggle around exactly on this line, so that each operation is getting also giving you the maximum rate. So, you are fulfilling actually two tasks. One is you are achieving higher conversions. While doing this, you are also ensuring that you are driving the reactions with maximum rates. So, you are getting maximum rates possible while you are also reaching towards higher conversions. So, you want to do it the most efficient way possible, achieving both objectives. You are getting here maximum rates, and also you are getting maximum rates, and you are getting maximum conversions as high as you can get. So, this is how you want to operate your reactors efficiently. Okay. So, this wiggling is all about going to higher conversion, but by having it on the right line, which is the maximum rate line, if you can wiggle around on the maximum rate line, then you are basically ensuring that you are also getting higher rates while operating your reactors as in interstage cooling operations. Okay. So, all of this is all coming from undergraduate understanding on CRE1, chemical reaction engineering from Levenspiel and Fogler. So, how do we apply an optimal catalyst design concept here on this same graph? How you are going to ensure further that while the catalyst is sitting in the reactor and all of these reactors are aligned in series in interstage cooling operation, you want to ensure as well that the catalyst is working in the best and optimal way. Okay. So, how do you ensure that and you further allow, you want to achieve maximum rates, you want to achieve maximum conversions, and you want to also ensure that my catalyst is performing in the best optimal way. Okay. So, here we come back to our Sabatier plots. These plots now can be plotted with different conversions. So, these are different conversions. So, 10% ammonia synthesis versus 1%, 0.1%, 0.01%, and they can be also plotted at different pressure and temperature conditions. And as you see that slightly the optimum will shift a little bit. So, it is shifting from -10 to let us say -40 for example, and you can see mostly ruthenium and osmium are on the top, while moly and iron are on the higher binding sites, and nickel and cobalt are on the lower binding sites. So, you want your catalyst whichever is there should be in the binding region, which is the window shown here, so that you get the catalyst operated exactly in that window. Now, you can plot the whole thing on the plots which we are discussing for the adiabatic reactors. Now, come back to this. This is your equilibrium conversion line, and you have also your maximum rates line. You can plot the window if you want to wiggle around. You can plot the window for optimal catalyst curves, which for example, at 80 bar with the N2H2 ratio 2:1 from the Sabatier plots is coming from -10 to -15 kilojoules per mole. So, between these pink and green line you have the window, you want to wiggle exactly on the maximum rate line, but you also want to be under this window of -15 to -10 in order to ensure best catalyst performance. So, this is all can be done in one picture together. While you are ensuring the best catalyst performance, you are also ensuring maximum rates and you are also ensuring maximum convergence whatever you can achieve from interstage cooling operations. So, how by theoretical modeling, while you are doing a very simple descriptor, whatever is adsorbing on the catalyst surface, hydroxyl, nitrogens for example, you are ensuring that this descriptor is explaining what catalyst and how the catalyst is going to give me the maximum turnover frequencies. That descriptor which is coming out from a theory like the density functional theory calculations is telling me how now I am going to operate my reactors using that catalyst under the right kind of conditions. So, you have already conditions ensuring that you should be running it at maximum rate line by adiabatic cooling operations, is interstage cooling operations, but now the theory is telling that you should be in the right window of best catalyst performance, okay, and this is the optimal catalyst curve. So, this is how you should be running. You should be running exactly, for example, here the conditions are changed 200 bar, their window here is -15 to -20, and in this window you really want to wiggle around and you want to do these, like for example, there are 3 adiabatic reactors as I can see, 3 adiabatic lines, and in between you are doing 2 interstage cooling operations and you are doing these operations and you have the right window where you are operating the catalyst, okay. So, here you are achieving 3 targets, one is the high maximum convergence as much as you can get, you are also ensuring that you are getting higher rates, and as well as you are also ensuring that your catalyst performance is running exactly at the Sabatier optimum, the maximum catalyst performance you can get, the maximum turnover frequency on the catalyst surface you can get exactly in this window. So, by applying ab initio or like the molecular level concepts, you can really run an industrial reactor. This is an example which is really explaining how you can run things by applying a molecular level concepts all the way to a commercial level industrial catalyst design. With this, I would like to conclude for 2 important readings for this understanding is the book which came out in 2014 on fundamentals of heterogeneous catalysis from Norskos group at Stanford, and really important review which I covered all the examples from this review is towards the computational design of solid catalyst published in Nature Chemistry in 2009. So, if you will read this, you will get the idea in a better way. But overall, this is presenting how you can use undergraduate concepts and how you can apply some of the modern concepts in molecular modeling together to achieve many things together, which is here shown that how you get maximum conversion, maximum rates as well as optimum catalyst performance. Thank you.